Hi everyone, in this video walkthrough, I'll be going over problem 3 on the trees exam prep discussion worksheet, and this problem is called an unintuitive game. So just kind of at a high level, what I'll be doing in this video walkthrough is first I'll be explaining how the game works, then I'll be kind of walking through the intuition for how we can translate this game into a game tree, then I'll be walking through the intuition of how we can approach pruning, and then I'll be formalizing that intuition with alpha beta pruning and then we'll proceed to the second part. Okay, so it's definitely going to be on the longer side of a video walkthrough, but I think it's really helpful for us to ground ourselves in the intuition for game trees and pruning. So yeah, hopefully it'll be helpful. But anyways, so the problem states, Sumer challenges Soham to the following game. In this game, there's a maximizing player and a minimizing player. Both players take turns adding numbers to the end of a sequence. The maximizing player wants to maximize the last number in the sequence, and the minimizing player wants to minimize it. Okay? So how the sequence is created is that on a player's turn, they take the previous number in the sequence and create the next number by either floor dividing the previous number by 2 or multiplying the previous number by 2 and adding 1. Okay, so our sequence will always start with the number 3, and it can only contain numbers in the range from 1 to 5. Okay, if a number goes out of bounds after an operation, it wraps around. So what this means is if I have the number 1 and I floor divide it by 2, this gives me 0. And 0 wraps around to 5. Okay, so the wrapping around is a little confusing, but you can kind of think about just if you have, we'll walk through some examples, it'll make sense. Okay, so finally, the maximizing player will always start and get 2 turns, and the minimizing player will get 1 turn, okay? So let's look at an example sequence. So let's say that we start with 3, because we always start with 3, and then the maximizing player goes first. So the maximizing player always has one of these two actions. So the maximizing player just decides to multiply by 3 and add 1, okay? So what this does, it gives us the next number 10 in the sequence. So our sequence so far, in this example, it starts with 3, then it goes to 10, okay? And then I'm gonna try to color code it a bit. So the maximizing player does the maximizing player's move and makes the next number 5. Then the minimizing player goes next, right? And the minimizing player chooses to floor divide 5 by 2 to get 2, right? So now the next number here is going to be 2. And that's because it was an action by the minimizer. Okay. And then the last thing here is that the maximizer gets 1 more turn. So the maximizer chooses to multiply 2 by 3 and add 1, giving us 7, which wraps around to 2. So what we see here is that the maximizer gives us 2. Okay, so the last term in the sequence we can see is 2. So this is the last term, and that is the term that the maximizer wants to maximize and minimizer wants to minimize. Okay, the last term here. So now that we have some idea how the game works, let's try to think of a strategy, just intuitively how you can make the best plan for the maximizer and the minimizer, right? If you're playing this game, the game is very unintuitive, right? But let's try to think of some sort of strategy together of how we can think of a way for the maximizer and minimizer to do the best they possibly can, right? Well, one idea I kind of have is since this game will always include 4 terms in the sequence, what if we consider every possibility for any sequence that could be created, right? So that idea is going to create a game tree. So what we're going to do, this tree may look a little intimidating, but the idea is that we want to use a game tree so that we can map out every possibility in the game for what could possibly happen, okay? So that's what we're going to use the game tree for. And using this game tree, we can figure out the optimal play for each opponent, the maximizer and the minimizer, right? So usually in a game tree, what we do is that we have minimizing nodes, and then we also have maximizing nodes, okay? So these are maximizing, and the green ones are minimizing. Okay? So when we're looking at this tree here, how would we approach filling out this tree? So this game tree is a bit different than a conventional game tree. In a conventional game tree, we only really store these triangles. But in this game tree, since it's actually like following a real life game, it's helpful to also store the current number in this sequence, right? So next to each one of these nodes, we're going to store the current number in the sequence, right? So let's just start filling it out. And I think it'll make more sense. Okay, so our sequence always starts with 3. And the maximizer who plays first has 2 options. The maximizer can either floor divide by 2 or multiply by 3 and add 1, right? Which kind of leads us into 2 different second numbers in the sequence, right? So if I'm at 3 and I decide to floor divide by 2, it'll give me 1 as the second number in the sequence, right? If I'm at 3 and I decide to multiply by 3 and add 1, it'll give me 10, which wraps around to 5, right? So it'll give me 5 as the next number in the sequence. Okay, so now let's say, let's look at this branch here. So if I'm at 1 and I choose to floor divide by 2, it'll give me 0, which wraps around to 5, right? If I'm at 1, I choose to multiply by 3 and add 1, it'll give me 4, right? This is just kind of mechanical, us filling out the game tree together, right? If I'm at 5 and I choose to floor divide by 2, it'll give me 2, right? And if I'm at 5, I decide to multiply by 3 and add 1, it'll give me 16, which wraps around to 1, right? Okay, so now we just have to fill out all of these leaf nodes here. Okay, so these leaf nodes represent the last number in the sequence, right? And it turns out that the last number in the sequence is also what we want to maximize or minimize, right? So when we're looking at all of these last terms in the sequence, all we do is we just say if I'm at 5 and I decide to floor divide by 2, what does that give me, right? So I'm at 5. We know that 5 maps to 2 and 1, so I can just fill that in here. And by similar logic, we know 1 maps to 5 and 4, so I can fill that here. And if I'm at 4 and I decide to floor divide by 2, it'll give me 2. If I'm at 4 and I decide to multiply by 3 and add 1, it'll give me 13, which maps to 3. Then if I'm at 2, right, and I decide to floor divide by 2, it'll give me 1. If I decide to multiply by 3 and add 1, it'll give me 7, which also maps to 2, right? Okay, so now that we've basically mapped out every possible sequence, right? And just kind of looking back at our example and kind of understanding how our example ties in here. In our example, we created this sequence, right? Shoot. Okay, that was much slower than I expected. But yeah, in our example, we created this sequence. And what we can kind of see here is that this sequence, right, corresponds to this branch in the tree, right? So what we've successfully done in this game tree is we've encoded every possible sequence that this game could possibly have, right? That's what this game tree is showing us, okay? So I think that's really cool, kind of taking this game and kind of decomposing it into a game tree so that we can try to figure out the optimal strategy for both players, right? So now that we have this game tree here, the next thing to do is to figure out what's the optimal strategy for both players. So how we want to proceed is we want to fill this game tree from the bottom up, right? And the reason there is that when I'm at this stage in the game, it's very clear what the optimal strategy is for the maximizing player, right? So if I'm at this point in the game, right, where the maximizing player has the sequence is 3-1-5 up to this point, and the maximizing player is deciding what to do for the last term in the sequence, right? The maximizing player can either get 2 or 1. So if I'm the maximizing player, I want to maximize the last term in the sequence. So what I'm going to do is I'm going to choose to floor divided by 2. And what we'll say is that the value of the node is 2. Okay? So the value of a node refers to what the value of the maximizer is if the maximizer decides to play optimally, right? And we're saying the value of the game is the last term in the sequence because that's the objective, right? The objective is to maximize or minimize the last term in the sequence, okay? So the idea, just once more, is that if I'm at a maximizing node and I have two options, I can either divide by 2 to get 2, multiply by 3 and add 1 to get 1. I would rather divide by 2 so that we can see that the value of this node becomes 2, right? Because that's the best play for a maximizer in this situation. And what we can kind of do is just kind of fill in all of these maximizing nodes at the bottom level by the same logic, right? So what we can do here is just kind of choose the maximum of all of these pairs to push up, right? Okay, so with this in mind, we can kind of do the same logic just for the minimizer in reverse, right? So the minimizer says, okay, if the sequence up till this point is 3-1, I have two options. I can either divide by 2 to give me the next number of 5, or I can multiply by 3 and add 1 to give me the next number of 4. And the minimizer knows that if I were to do this possibility, the maximizer optimally would choose and get 2, right? And the minimizer sees if I were to multiply by 3 and add 1, the maximizer at this point in the game would decide, hey, it's best for me to multiply by 3 and add 1 to give me 3, right? So the minimizer sees that these two options here, and the minimizer says, I would rather go down this route. So the value, assuming the maximizer is playing optimally, which we always assume for both the maximizer and the minimizer, is that this value is 2 here, right? Because we're taking the minimum of these two possibilities, right? And by the same logic, if we're looking at the minimizer in these two possibilities, the minimizer would obviously divide by 2 here so that the maximizer can only choose from 1 and 2 as the last numbers in the sequence, right? So we can fill in 2 here because that's the minimum of these two values. And then finally, when we're looking at this root here, right, the root should be the maximum of these two, but since they're the same, it doesn't really matter which choice the maximizer takes, because either way, the maximizer is getting a value of 2. And what this game tree is kind of showing us is that if the maximizer and the minimizer both play optimally, the last number in the sequence is going to be 2, right? So I really, really think this is important for that to sink in. So if you're kind of confused about it, try remembering why we draw the game tree, right? The reason we draw the game tree is we want to consider every possibility of the game, right? Then after considering every possibility of the game, we want to figure out what's the optimal strategy for each player. To figure out the optimal strategy for each player, what we do is we fill this game tree up from bottom up, right? Okay, so now what we're going to do is we're going to introduce this idea of pruning, right? So what I'm going to do is I'm going to kind of copy this down. Okay. So I'm just going to redraw this to make it a bit nicer. Let's make a cool triangle. Okay, give me a second. Okay, my drawing skills aren't exceptional. Okay, so I'm just kind of redrawing this tree. And then we have 2, 2, 2, 2, 3, 2, 5. And then we kind of need little boxes at the bottom. Okay, in hindsight, I could have drawn this out in advance, but we're getting there, we're getting there. Okay, so and the values at the bottom are going to be 2, 1, 2, 3, 1, 2, and 5, 4. Okay, so the reason I kind of redrew this whole tree is just because we don't really need all of these values filled in. Okay, I'm actually going to take out these values too. So the idea behind pruning is that when we're creating this game tree, let me kind of write this out as I'm going. So when we're thinking about pruning, our main intuition here is that we don't always need to consider every branch of the tree. Okay, so what do I mean by this? Well, let's try to figure out how we can accomplish pruning together, and then we'll formalize that with alpha beta pruning. Okay, so looking at this game tree, right, what we're going to do is we're going to try filling it out in the same way that we did last time. Okay, well, what we did last time is that we started the root and then we go down to the first leaf node, right? So when I'm at this leaf node here, then I look at both leaf nodes and then I assign the maximum to be 2 here, right? Then what I'm going to do is I go up to the parent and then I have to explore this right node. And then what we see here is that when I'm trying to find the value of this maximizing node, what I'm going to do is I'm going to look at this left child here. And at this point in the algorithm, we're going to see something very, very cool happen. So what we're going to see is that when I'm at this node and I just looked at the node on the left, what we can notice is that we know that this minimizer, the minimizer is going to be, let's try to keep the color scheme consistent. No, my iPad's being laggy. Okay, so when we're at this minimizer right here, what we know is that its value is going to be at most 2, right? Because if I'm a minimizer and I have one option here that's 2, we know that the minimizer can only find better options in its other children, right? So what I can say about the value of this minimizer is it's at most 2, right? Then what I can say is that if I'm looking at the value of this maximizer here, after I see this number 2, what I can say is that the value of the maximizer is at least 2, right? And what we'll notice now is that we don't need to look at this child here, okay? So the intuition why I can ignore this child and all future children of this maximizing node is because this minimizing node will never choose this pathway because this one is equal or better, guaranteed. So what I mean by that is this minimizing node is guaranteed a value of 2 if we go to the left, right? And the minimizer realizes that this maximizing node will always be 2 or more, right? So at that point, the minimizer says, hey, there's no point for me to continue considering more leaf nodes from this maximizer because I have an equal option here, right? So I would rather choose that option, okay? So what we've successfully done is that we've kind of pruned the amount of the tree that we have to consider, right? So what we've done here is that we've said, okay, the value of this minimizer is 2, and we didn't have to look at this leaf node. Now you might say, hey, Soham, like you saved one leaf node, like whoop-de-doo. Well, when we look at like a really big tree in practice, we can actually prune a lot more, right? Kind of following this logic. But let's finish doing this game tree first. Okay, so now what we can kind of say here is that when I'm at the root here, okay, so if I'm at the root, we know that the value of the root is at minimum 2 because of this option here. So when I'm going to the right, then I'll go to the left here. And then what we'll say at this point is that we're at a maximizing node, and we'll look at the number 1, right? And then we'll look at the number 2, and we'll decide 2 is better, so this value is 2. Then what we can say is that this minimizing node is going to be at most 2. And at this point in the algorithm, what we can notice yet again is that we don't need to look at this whole branch here, right? So the reason we don't have to look at this whole branch is because when I'm at this root node, right, I'm guaranteed a value of at least 2 if I go to the left, right? So the maximizer at the root node says, hey, is it worth even considering options to the right? Because I know the minimizer at this node right here, its value is going to be at most 2, right? And since the maximizer is already guaranteed a value of 2, the maximizer has no reason to consider this minimizing node anymore, right? So with that reasoning, I can prune out this entire subtree. We don't even know the subtree actually exists, right? That's how pruning works. And what we'll say is that the value of the maximizer is 2. Okay, so now that we've kind of like built some intuition for how pruning works, what I want to do now is revisit this example with alpha beta pruning, which is the formalized algorithm for how we implement this pruning intuition. Okay, so let's bring these leaf nodes back. Okay, so what we're going to do is we're going to do the whole thing again, but we're going to do it with alpha beta pruning, right? So when we're looking at alpha beta pruning, what we're going to say is that alpha is going to be the best value the maximizer has seen from the path from the root. Okay, and then in a similar light, we can define beta as the best value the minimizer has seen from the path from the root. Okay, so alpha beta pruning really just leverages this intuition that we've walked through so far. So when I'm at the root, when I'm at the first maximizing node, what we're going to do is we're going to set alpha equal to -infinity, and we're going to set beta equal to +infinity. And the reason for that is that when I'm at this root node, the best value the maximizer has seen is nothing, right? The maximizer hasn't seen anything, so we denote that with negative infinity. And the minimizer hasn't seen anything, so the minimizer's best bet right now is positive infinity, right? So then what we're going to do is we're going to go to this node right here, right? And alpha and beta are the same values. Okay, then what we're going to do is we're going to go to this left node, and they're still the same values, right? Now what we're going to do is when we're at this maximizing node here, and I see a 2, what that's telling me is that for this maximizing node, its new best bet is to choose 2 instead of negative infinity, right? So now for this node here, the alpha value is going to be 2, right? And then what we'll see is that if I'm looking at this value here, we'll see it's not better than alpha. And what we're going to do is that we're going to solidify the value of this node as 1. Okay? Now what we're going to do is we're going to exit this function call here and go back up to the function call right here. Okay? So now what we're going to do is we know the value, shoot, I messed this up. This value should be 2. We know the value of this node is 2, right? So we're passing that value up here. And now the minimizer says, hey, if I go to the left, the best thing I can do is 2, right? So what we're going to do is we're going to choose beta to be 2, right? Because the minimizer at this node is guaranteed a value of 2 if I go to the left. Okay, so now what we're going to do is we're going to say, okay, let's try going to the right. So if I go to the right here, then what I'm going to do is I'm going to look at this node here, right? And when I look at this node 2, what we'll realize is that 2 is better than negative infinity, right? Because we're the maximizing node, so we deal with alpha. So what we'll say here is that we'll change this value to 2, okay? And now what we're going to do is that we're going to notice that the best value the maximizer has seen, right, on this path is 2. And if we're looking at the best value the minimizer has seen, it's also 2. So if it's ever the case that alpha is greater than or equal to, actually let's put that in a different color. If alpha is ever greater than or equal to beta, then we prune. Oh shoot, I don't know why that made it into arrow. Okay, so that's like our pruning possibility. Hello, hello. Oh no, I lost my iPad. Okay, yeah, so just coming back here. When alpha is greater than or equal to beta, we prune, right? So if I'm looking at alpha and beta here, we see that if alpha is greater than or equal to beta, which is the case here, then we're going to prune this tree or this branch. So we're not going to actually consider the right child. And the intuition, it's the same thing that we were doing before, right? We just kind of formalized it in terms of alpha and beta. So why is this the same as we did in the previous run? Well, what we're doing here is we're saying, hey, if I'm at this part of the tree and I'm looking at my right child 3, then what's the case is that the minimizer in the node above was guaranteed a value of 2. And as this maximizing node, I'm guaranteed a value of 2 as well. So what we'll see here is that it doesn't make any sense for the minimizer to consider this child because the best value the minimizer has seen so far is equal to the best value the maximizer is currently looking at. So it doesn't really make sense to consider this possibility, right? Okay. So now what we're going to do is we're going to fill up this with 2, okay, because we choose this option here. And then what we're going to do is we're going to go up to this call here, and we're going to pass in the value of 2 to alpha, right? Because if I'm at the maximizing node here, I'm guaranteed to get at least 2 if I go to the left, right? I'm guaranteed to get 2. So then if I go to the right, then I go to the left, we're going to continue with our alpha and beta. Okay, let's make that a bit smaller. Okay, so now that we're here, let's pass alpha and beta down again. Okay, so alpha is 2 and beta is positive infinity, right? Then what we do is we pass them down once more. Okay, so what we're going to do here is we're at a maximizing node, right? So we're going to consider, hey, is the left child better than alpha? And then we'll see here that alpha is 2 and our left child is 1, so we don't actually update alpha. Then we see left child is 2 and alpha is 2, so we don't actually update alpha again, because we only really update alpha if it's strictly better. So then what we'll do here is we'll put the value of this node as 2, okay? Now what we're going to do is we're going to send this value of the node back up. And what we're going to do is set beta equal to 2 here. And again, what we'll notice is that since alpha is greater than or equal to beta, we know that there's no reason for this node to consider this subtree here. So we're going to prune it off like so, okay? And then we'll pass this 2 up, and then we'll complete the game tree by taking the maximum, right? Okay, so yeah, hopefully that kind of made sense, like how we translated the intuition into the alpha beta pruning algorithm. And in the next part, we'll continue this problem. So I'll pause here, and yeah, thanks for watching.